Now let's understand a power frequency of the over voltages in the power system means it is subjected to 50 and the 60 hertz of the system. So we know that the power frequency of the over voltage which is going to occur in the power system, they are much more concerned in the case of EHV system like if the voltage is around 400 kV and above. Some of the main causes which is going to be some of the causes for the power frequency and its harmonics over voltage are given below. So these are the four things. That is, first condition is sudden loss of the loads, okay, subjected to the normal power. Then we have disconnection of the inductive loads or connection of the capacitive loads. Then we have Ferranti effect and unsymmetrical faults. Ferranti effect is nothing but receiving end voltage is greater than the sending end voltage because of the transmission line behave like as a capacitance. So then we have unsymmetrical faults, so like line to line, line to ground, line to line, double line, three phase, all the things, not three phase, double line to ground faults. Then we have saturation in the transformers, etc. So, however, these over voltage subjected to the power frequency of the harmonics with a frequency which is near to that the operating frequency, which are going to cause during the tap changing operations by magnetic or ferroresonance phenomenon in the large power transformers. So resulting in there is a resonating over voltage due to series capacitors with the shunt reactors or the transformers. So duration of these over voltages may be from 1 to 2 cycles, or sometimes it may be a few seconds depending upon the over voltage protection which is going to employ. Let's understand one by one, that is sudden load rejection. Okay, so let's consider there is a generator which is connected to the transmission line. Okay, and some of the load which is connected to that. Okay, so this is generator G, right? So whenever there is a sudden load rejection on the transmission on the power system, so resulting in so this generator which is going to couple with the prime mover. Okay, this is a prime mover. There is a contact. There is an coupling between a generator and the prime mover. Okay, there is a intercoupling between these two. Okay, this is nothing but we can call it as coupling. So whenever this is a load increasing, the prime mover has to take into consideration. If there is a load rejection, means load reduces, this prime mover has to reduce the what is the total input which is given to the generator. So if the first condition is if suddenly this load rejection, if it is discontinued at this point, okay, we are considering this is some fault at this point, what will happen to your generator? So we know that if there is a sudden load rejection, the speed governor and automatic voltage regulator will uh, will do a action to restore the normal condition. But initially, what will happens? But initially, both the frequency and the voltage, both the frequency and the voltage is going to increase, and approximate voltage rise, which is given by the equation V is equal to F divided by F naught into E dash in bracket 1 minus F by F naught XS and XE. The XS is nothing but the reactance of this generator, which is the summation of the transient reactance of the both generator and the transformers, and XC is nothing but the capacitor reactance of the line at the open at increasing in the frequency, and E dash is nothing but the voltage the generated before the overspeeding of the prime mover and the load rejection, and F is nothing but the instantaneous increase in the frequency. F naught is nothing but F naught is subjected to the frequency of the normal. Okay, so if this increase in the voltage, it maybe goes as high as 2 times of the per rate value. If the system voltage is around 400 kV of the line. Then the voltage at the sending end, which is going to affect by the line length and a short circuit MEA at the sending end bus and reactive power generation of the line, because we are going to considering both line capacitance, reactance and the shunt or series capacitors, all those together. So hence this shunt reactance, which is going to reduce to 1.2 to the 1.4 times of the Poret value. Next one is Ferranti effect, that we know that if there is a long uncompensated transmission line, this is going to exhibit there is an voltage rise at the receiving end. The voltage rise at the receiving end V2 is approximately, this is V2 is approximately, which is given by V2 is equal to V1 divided by cos beta L. So V1 is nothing but a sending end voltage, L is the length of the line, beta is nothing but phase constant of the line, which is given by this equation. So this is the approximate a typical uncompensated long transmission line having some generators, okay, source of the EMF and this inductance and the resistance and the shunt capacitances of the long transmission lines. Okay, about 6 degree, if you are considering per 100 kilometer of the line at 50 hertz of the frequency, okay, by considering R, L, G, C, that's nothing but resistance, reactance, shunt, conductance and the capacitance, which is discussed in the previous subject. That omega, what we considering is angular frequency for the line. So uh, considering that line capacitance is concentrated at the middle of the line under open circuit condition at the receiving end, then there is a line charging current, means this is the open circuit at the middle end, and there is a line charging current which is given by IC is equal to j omega C into V1, that's nothing but V1 divided by XC, and uh, the voltage V2 is approximately, which is going to be equal to V1 into 1 minus of XL by 2XC. XL is nothing line inductance, line inductive reactance, and this is the line capacitive reactance. From this approximately, from this approximate equation, which is going to give a better approximation when the line distributed parameters like RLGC, RLGC resistance, reactance, and conductance, capacitance per unit length are known. This is equation which is going to give a more accurate value for the to calculate the Ferranti effect subjected to the lightly loaded conditions. Next one is ground faults and their effect. So if you considering that this is the vector diagram of an open circuited uncompensated line of some Ferranti effect, okay, at the middle point we are considering the capacitance, so this is reactance which is 120 by, so this is a phasor diagram which you can see here. So if there is in some single line to ground faults, which is going to cause there is a rise in the voltage in other healthy phases. So usually with solidly grounded system, the increase in the voltage will be less than the line to line, means that if it is properly grounded, the voltage will not be greater than that line to line voltage. With effectively grounded system, which is given as x0 by x1, that's nothing but x0 and r0 values are subjected to the zero sequence value of the reactance and the resistance. X1 is nothing but positive sequence reactance of the system. So hence the rise in the voltage of the healthy phases usually does not exceeds 1.4 times of the per unit value of the system. Next one we have saturation effect. So whenever the voltage above the rated value are going to apply to the transformers, the magnitude of the magnetizing current increases rapidly and maybe about of the full load rated current for 50% of the over voltages. So thus The magnetic current are not in the formation of the sinusoidal in nature, but are also will act like in peak waveforms. So the third, fifth, and the seventh harmonic contents may be of 65 percentage, 35 percentage, and 25 percentage of the exciting current of the fundamental frequency, which having the corresponding to the voltage of 1.2 100 values. For the third and its multiple of the harmonics, if we are considering zero sequence impedance values are going to be more effective. And if we are connected apart from a star to the delta, then the windings which is going to separate that we understood in the past analysis that. So if there is a fault current, all the current which is trying to pass into the legs of the transformers. But in the case of the shunt connected capacitors and the line capacitances, which is going to form a resonance circuit and will cause high third harmonics of the overvoltages. So, so when such overvoltages are going to added, that's nothing but the overvoltage is going to rise in the lines, may be significant. For higher harmonics, there is a series resonance between the transformers, inductance, and the line capacitances will occur, which maybe produces even higher voltages. So that's why subjected to that the inductance and the behavior of the line capacitances, which is going to be a more effective when we are dealing with subjected to the over voltage in the over voltages and the lightning voltages in the uh, system. So that's why subjected to that the EHV and UHV of the switching surges is plays a great role of studying the characteristics and how we are going to minimize this effect is placing an important role for the designing of the power system.